Hi, this is Clark Hyland. It's great to be able to present on nonlinear seismic analysis and other uses of Abaqus projects that we've been involved in over the last few years. I just want to acknowledge Zhu Li, who's been my assistant in a number of these. Okay, so we've been doing a number of projects. One of these is fire responsive structures for the burnout condition where the sprinklers are assumed not to be operational, and the effect of this can mean that safe egress paths or perhaps stairs that might be supported by composite steel beams and floor slabs may be susceptible to deformations that could lead to smoke or breach of fire line walls, say jib walls, and also potential collateral damage and even perhaps leading to collapse of egress stairs. So this is something that needs to be worked out. So we've used Abaqus to analyse the what's happening in terms of deformations of slabs under fires using gas time temperature curves that we've had from fire engineers. We then apply that into the Abaqus using heat transfer analysis functions, and then do deformation analysis following on from that using the temperatures that have been derived. So some of the findings we get from that is we get the temperatures in the beams. Say in this particular example, we're getting up to say 669 degrees in the lower parts of the steel beams. Okay, so we then do the thermal stress analysis, and what that shows here, for example, is the cleats and the ends of the webs get crumpled, and we get failure developing there. So we get combined stresses, in the von Mises greater than what is allowed. So potentially we're getting failures that may lead to collapse of those beams. The other interesting thing there, it just shows how important it is to slot the holes of these beams. That can release some of the thermal stresses that are developing. Okay, another project where we've used Abaqus is plate girder buckling analysis. This was done recently for a project we've been involved with in Melbourne. And so it's the Caulfield to Dandenong level crossing removal project, and there's about just over 2 kilometres of elevated viaducts, 40-metre spans made of post-tension box girders, concrete box girders, and we work for DL, who have designed and manufactured the bridge construction equipment pictured in the slide. So we managed the design verification and design registration with SGS New Zealand, doing the mechanicals and overall design registration and design verification sign-offs, and us doing the structural aspects. So this equipment's pretty massive. We've got 430 tonne lifts that are being done by this equipment. So the full 40-metre spans are lifted and then transported by the launching gantry along the portions that have been already built, and then the precast spans are lowered onto the piers. So you can see a picture of a man there. There's the size of the tyres, so you can get a bit of a feel for the scale of it. Okay, so the launching sequence of this is launching gantry moves along the viaduct, then comes to the edge where there's a support beam. That's roughly about 2.9 metres deep and a metre or so wide box girder that has been launched out already ahead of it over 2 spans. The gantry then then mounts the support beam and is then pulled along or driven along the support beam until it gets past the next support, at which point it then basically drives the support beam out of the way, clears the way, and so there's a space there for it to lower the concrete girder into the space there. And so once that's lowered, it can then come back off the support beam and drive back and pick up another one. Moves at a cracking pace of 2.5 kilometres an hour when it's fully loaded and 5 kilometres when it's unloaded. Okay, here's some photos of it actually in operation at the current time. So here it is picking up the precast box girder. One of these is basically one railway line for each of these. There's two viaducts being built either side of the existing railway line. Okay, and here it is travelling across portions already built. Here's the cars at peak hour, very pleased that it's working and making the railway nice and clear, the roads nice and clear so they can go to work. And here's a view of the support beams that are cantilevering out past over the temporary supports, waiting for the gantry to be driven along and place the next beam. Here's the gantry mounted on the support beam, and it's actually driven the support beam out of the way, cleared the way so it can lower the precast concrete girder down onto the piers. Okay, so quite a few challenges doing this design verification, and one of the ones that came up was using AS 5100.6, which was the standard we were reviewing the design against. Gave different answers around what the level of minimum thickness of plate should be in the web, the compression zone, and because 8mm had been used, this was outside what was allowed by AS 5100.6, but was allowed by the rules that the equipment had been manufactured to in Europe. So to get through this issue, potential for perhaps some buckling in the webs, it was agreed that DR would use a finite element model to verify that the loads were able to be adequately supported, and we also did the same as a verification using Abaqus. So to do that, you have to use the imperfection, put a pre-buckled imperfection into the model. So we went through Abaqus and chose a mode. In this case it was actually mode 19, and then you amplify this to the size of defect that is required in 5100.6. So this is what we thought would be the sort of buckling that we'd expect in that zone. And then we ran the post-buckling analysis, and we found this was the resulting deformation. So we were getting some buckling in the top where the compression was, but we're also getting a little bit of buckling mid and lower below the neutral axis, which wasn't really what I was expecting. But when you think about it, if you're getting a buckle up here, then it's got to be matched by another buckle somewhere else. So the upshot was that we were able to verify that DR's assertion that the gantry box girder was able to safely hold the maximum loads without any potential for collapse was verified, and that was
great use of Abaqus. So another thing we've used it for is cyclic nonlinear analysis and seismic. So here's a building that we analysed. It had been through an earthquake, and there were some questions about the deformations of the EBFs, eccentric brace frames, and whether or not these could be repaired, or whether they could take another similar size earthquake. So what we did was model the building using Abaqus. So there was some moment frames, a couple of directions. We used beam elements for the moment frames, and used elastic properties, these red bits, and inelastic properties in the potential yielding zones. So that was the reason for doing that, was to minimise computing time. And we put in the slabs as shell elements. These were ribbed to give an equivalence to composite steel beams being there. So we were just wanting to have trying to avoid any potential for slab modes of vibration if we were to use dynamic analysis, and then we didn't. Particularly what I did here was a cyclic pushover analysis. So yeah, so sort of reloading. So the question was, would these hinge zones at the links be able to sustain another earthquake? We knew that at level 6 of the building, what the peak rotations were there, and we'd also had a look at what the cracking in the slab was, and this indicated a certain amount of deformation. We then sort of tried to replicate that with rotations of these links, and just to see how the strain built up in them. We also knew from the location of the building and the way buildings with similar natural frequencies had performed in the earthquake that there were a couple of strong displacements, cyclic displacements, perhaps 4 times the first one, and so we sort of used this to come up with a bit of a synthetic cyclic reloading analysis, and had a look at what tried to benchmark that against the actual deformations we measured on site for these. So the results were quite interesting. It showed us that we had plenty of capacity remaining in those links, and in fact the second reload of these, when we broke the material properties up into 4 subsections within each of the links, where we used the strain results from the first analysis to say this was the pre-strain level that it effectively got to, and then used steel properties starting with that level of pre-strain back in the model, so that we could see when we ran the second analysis whether it would survive or go worse. In fact, what it showed is that it performed better in the second earthquake than in the first, because there was less inelastic deformation. So it was an interesting result. We also came up with some repair options, including thermal stress release for some of these, to improve the properties of the steel, and went from there. So yeah, so we've done. It's just a summary of three good projects that we've used Abaqus on, and found it excellent. Appreciate the support we get from Amy at SIMULIA, and appreciate the opportunity to be able to present.